Okay, we are going to start part 7, Sculpting the Surface, Ice, Wind, and Coastal Processes, our final part of our book as we wrap up this class. I hope you enjoyed it. If for whatever reason my mic cuts out, let me know through the chat or through the microphone. I had an issue a couple weeks ago with that, but I think it's worked out. So first of all, we'll start by talking about glaciers. There are different kinds of glaciers. First of all, let's go to the very beginning here. Glacial erosion and deposition. This particular picture is on the Tunsian Glacier in Alaska. You can see that at the bottom of it, there's a little bit of rivers and water coming out. That's kind of where the glacier has lost some ice and it's melting, and then it's turning into water and forming small rivers at the bottom. This is a glacier, like many, that's been retreating and becoming smaller due to global warming. And this is in a valley in Alaska here. So glaciers are part of the cryosphere. Those are one of the 5 main spheres that we've studied, including the biosphere and the others. And glaciers are, of course, made up of frozen bodies of water. The cryosphere is all forms of frozen water: snow, icebergs, ice sheets, glaciers, and so on. And glaciers are bodies of ice formed on land that are in motion. Glaciers move generally very slowly, too slow most times for people to be able to see. You can measure them over months or years. A fast glacier may move a couple of meters per month, but generally they move quite slowly. And they can either slide or they can kind of move by bending within the body of the glacier. Erosion takes place at the bottom of glaciers, and that can be hard to witness. So unlike rivers, glaciers can be more difficult to study than rivers, because you can't always see what's going on, since much of it is happening at the bottom of the glacier itself. So there are different kinds of glaciers. The 2 main kinds are mountain glaciers and continental glaciers. Mountain glaciers are ones that you would have in mountains, sometimes called alpine glaciers. And those are broken down into roughly 2 categories: the cirque glaciers, which are kind of up in the mountains in these carved out sort of amphitheaters in the high mountain areas that are filled with ice, kind of like bowls that get filled with ice high in the mountains. And then the valley glaciers, which are lower in the mountains, that are at the base of the mountains typically. And then in addition to mountain glaciers, there are continental glaciers, or sometimes called ice sheets. These are very large land masses covered with ice. The only ones we would have today that would be like that would be Antarctica and Greenland. Those are the only continental glaciers we currently have. This is Greenland. Greenland is the largest island in the world. Australia is not considered an island. It's considered a continent. You know, the cutoff between an island and a continent is somewhat arbitrary, but Greenland's considered the largest island in the world. It's about the size of Mexico. It actually has a population of 56,800 people, which is fairly small considering its massive size. And Greenland is actually part of the Kingdom of Denmark. Denmark and Norway both colonized Greenland in the 1600s and laid claim to it. Then Norway gave up its claims in 1814, and then Denmark fully integrated Greenland into the Danish state, but it has autonomy. So it's part of the Danish country, but it has self-governed, sort of like we would have with Guam in the US or Puerto Rico. So technically it's part of Denmark, and home to about 56,000 people. Antarctica is just under twice the size of Australia. It's larger than a lot of people realize. It's colder than the Arctic because it's over land. And as we've studied, water has a moderating effect on temperature. So ice that is over a body of water, the Arctic Ocean, will be colder than ice that's over a landmass in the Antarctic. So it's fairly large, and it's colder than the Arctic. And there's a very interesting TED Talk that talks about the Arctic versus the Antarctic. So if you haven't watched that, make sure you take a look at that. Antarctica has no permanent towns or cities. It does have a small collection of permanent scientists that study usually ice and global warming and so on there. So there are always a few scientists down there, but no large permanent settlements. So glaciers have started to become more common at the beginning of the Pleistocene, or the Ice Age. This is a period of time that started roughly 1.8 million years ago, going up to about 10,000 years ago. So it's a fairly long period of time. And within this period of time, there have been dozens of ice ages. Scientists thought at one time they could try to predict about how many there were, but they can't really. Over 1.7 roughly million years, 1.8 million years, there have been dozens of ice ages that have come and gone. The most recent one peaked about 20,000 years ago and receded about 12 to 10,000 years ago. So including the last ice age was in the late Cenozoic era, And that began about the late Cenozoic era began about 3.5 million years ago, and then later came the Pleistocene era, and then the Ice Age, about 1.8 million years ago to about 10,000 years ago. So glaciers form by snow coming down, and it often can build up over a long period of time. Snowflakes begin and they land, and at first, when snow piles up, it's kind of fluffy. There's a lot of air in it, but over time, it can get compressed and condensed, and the shape of the snowflakes break down. They lose their distinct 6-point shapes, and then they become smaller and more compact. Then, when they're partially compacted and the edges of the snowflakes have been worn down, it's called firn. And then as it continues to get condensed and compressed, it becomes glacial ice. So firn is kind of the midway point between a pile of snow and glacial ice, where it's partly formed into a glacial ice, but hasn't quite done that yet. So ice accumulation and ablation. Ablation basically means ice lost from melting or other things. It's common for glaciers to have a zone of accumulation where it builds up ice, and a zone of ablation where it loses ice. So typically higher up, it's colder, there's more snow that's building up, and glaciers gain mass higher up in the glacier. And as you get further down, it gets a little warmer. Then you have glaciers melting and shrinking. So melting is basically a phase where, again, solid becomes a liquid. Sublimation is the phase that changes solid directly into gas. That can happen sometimes with glaciers. It'll go from ice directly into gas. And then calving is when you have a large chunk of an iceberg or a glacier that breaks off from the rest of the glacier. So those are all examples of ablation, melting ice, sublimation, and calving. So glacials move. Again, they usually move fairly slowly. There are two main ways they move: glacial creep, and that is when the glacier does not slide, but it kind of moves. The body of the glacier moves over time because of gravity. And this diagram demonstrates that. Usually glacial creep is most significant in the center of the glacier and less so along the edge of the glacier where it's up against the bedrock. And then there's glacial sliding, and that's movement where usually it's a little warmer. There's some melting, there's water underneath the glacier that provides some lubrication that can make it slide a little bit. And that's when the whole glacier slides and doesn't just bend and move as a whole. And on rare occasions, you'll have something called glacial surge, and that's where you have a rapid movement as much as 1 meter per hour. For a glacier, that's really fast, and that's very unusual, but it can happen occasionally. So temperature and glacial movement, generally the warmer it is, the more likely you are to have glacial slide, and the cooler it is, the more likely you'll have glacial creep. This diagram kind of shows glaciers move down the mountain. They're pulled by gravity the same way water would be. And it's common for glaciers to have little breaks in the top of them called crevices or crevasses. And those are the big gaps in the tops of glaciers that form as glaciers move. This here is a picture of some crevasses in Greenland, and these can be very dangerous if you have to move across them. People who ever have to cross glaciers for whatever reason, they're scientists or something, need to be very careful. This is a picture on the bottom right of a scientist actually crawling down into one of the crevasses, looking up. So these are big breaks in the glacier. So glacial erosion, we've studied erosion, that's the breaking down and moving of particles. Glaciers have some major kinds of motion and erosion. One of them is called plucking. That's when the movement of the glacier pushes up and breaks up large chunks of rock, as you can see on the top there. And then there's abrasion, and abrasion is when rocks inside the glacier hit against the bottom of the rock, causing more breakup and more erosion. So plucking is when the ice itself breaks rocks away. Abrasion is when pieces of the rock brush up against the rock bed and cause more abrasion. Striations are linear gouges that are caused by rock debris in the glaciers. And then there's an unusual rock formation you see on glaciers sometimes called rochers montanais. And those are asymmetrical mounds that form, as you see in the diagram, where glaciers will move. They'll deposit some of the rocks that they've broken up on the leeward side of this rock. And kind of like a sand dune, it builds up a small pile. And then striations are large gouges, again, that we've seen. We'll see in a picture here. These stripes are basically gouges that were caused by the glacier as it was moving. And you can see the movement of the glacier, where it was going by the directions of these scrapes, these striations. And then this is an example of a rocher montagnais. And as you can see on the left is where the glacier would have been moving from, and then towards the right, the leeward side of the glacier is a little higher, where it would have deposited some of the rocks the glacier was carrying inside of it. So landforms and landscapes of continental glaciers. We talked about mountain glaciers. Continental glaciers, of course, include Antarctica and Greenland at the moment. These mountains are trans-Antarctic mountains. Most of these are submerged by the thick layers of ice they have in Antarctica, some of which are 2 or 3 miles thick in spots. But some of the higher peaks can peek through these massive glaciers and be seen from the sky. So ice sheets, the past and present. The last ice age peaked about 21,000 years ago. And the picture you have here shows the extent where scientists think it might have gone to. This is basically the Alaskan Peninsula, and these are the Aleutian Islands. So this is the possible maximum expansion of glaciers along Alaska. Because there was so much ice that was locked up in glaciers, sea levels were actually significantly lower at the peak of the last ice age because so much ice was stored in glaciers, causing sea levels to lower. So this is Antarctica ice sheets. Antarctica ice sheets have large sheets of ice that kind of move in specific directions away from the center towards the ocean. And that it can be fairly fast moving. Sometimes these are called ice streams because they behave somewhat like water does. And they go from the center of Antarctica to the ocean, to the Southern Ocean, where it's a little warmer and a little lower. So it just kind of follows gravity. And when you have these large ice chunks meet up with the Antarctic Ocean or the Southern Ocean, it can cause calving, which is the breaking up of ice as we see here. And that's increased significantly lately because of global warming. You'll have more calving in Greenland as well as Antarctica. So it's pretty spectacular if you can see it. Some Alaskan cruises will cruise along glaciers in Alaska and see large chunks of ice break off into the water. So they're pretty interesting. Greenland's ice sheets is only 1/8 the size of Antarctica, but that's still fairly large. It contains about 11% of the world's fresh water supply. The Antarctic ice sheet actually covers 9% of all the land on Earth, so that's fairly large, 9% of all the land. Greenland's about 1/8 the size, and it contains about 11% of the world's fresh water supply. Much of the rest is in the Antarctic glaciers or other glaciers. So North America and Eurasia at the peak of our last ice age, about 20, 21,000 years ago, had a very large ice sheet that covered it called the Laurentide ice sheet. And that basically covered almost all of Canada and much of the Midwest, including most of Michigan, helping create the Great Lakes. And then in Eurasia, in Scandinavia, and parts of Russia, they had the Scandinavian ice sheet. And that was almost as large as the North American Laurentine ice sheet, and that covered much of Scandinavia and northern Russia. So at the peak of the last ice age, there were real large portions of North America and Eurasia that were covered in ice. Interestingly enough, this kind of shows where the most recent, the Wisconsin barrier was, where it went to, the Wisconsin ice age. And then earlier than that, they know that there were glaciers that reached further south. There isn't as much known about those glaciers because they were a little older. But interesting, in Wisconsin, a large chunk of the south east corner was not covered by glaciers, and this is called the driftless area. I think I mentioned this, and I think we had a little article about it a little earlier. And different ice ages are named after the states that there's the most evidence to learn about them. So the Wisconsinite ice age is what the last ice age was called. And then the driftless area, this is an example of it. It looks a little different than the rest of the Midwest. Growing up, I lived in Oshkosh, Wisconsin, and we would drive to Mankato, Minnesota. And during Christmas, we would drive through this driftless region, and we'd see these weird rock pillars that look so different than Oshkosh, just 2 hours away. And it's because this area wasn't covered with glaciers, so it has a unique and different geography to it. So other landscapes shaped by continental glaciers. Here on this diagram, you see some landscapes like moraines and kames and kettles and so on. Kettles are basically kind of like potholes that are often filled with water, but they're gouged by glaciers, and they're fairly sharp, small lakes that form. A terminal moraine or a recessional moraine is basically a glacier extends, and as far as it extends to, when it doesn't extend anymore, often the glacier will deposit dirt and rocks at the edge of the glacier. That's called the terminal moraine. And recessional moraines are these little lines that form from deposition as the glacier was retreating. So terminal moraines and recessional moraines look like kind of long, skinny hills. And there's other deposition or things deposited by glaciers, including till. Till is basically poorly sorted deposits, meaning it's a combination of large particles like rocks and small particles together. And then there's outwash, and outwash is usually smaller sediments, not really large ones, but smaller sediments that are left behind at the edge of glaciers. So here's an example of till on the top there. You can see lots of unsorted big rocks, small rocks, lots of different kinds of minerals and lots of different kinds of color for dirt. And on the bottom right, more consistent, that's outwash with specific stratified layers and a lot finer dirt that is made up of outwash. So a little bit more about moraines. This is a diagram of a moraine showing what a terminal moraine would be on the top, and then a recessional moraine on the bottom. Recessional moraines again form as the glacier is retreating. And then also unusual formations caused by glaciers are drumlins. And these are long linear hills formed by glaciers depositing dirt and rock as it retreated from a specific area. And like with the striations we studied, you can kind of tell the direction the glacier was moving in by the long nature of these hills. This is a topographic map of one. And this is a drumlin in real life. I think this is in Wisconsin. And they have these unusual kind of long, narrow hills that form in parts there. This is a kame, K-A-M-E. These are also common in parts of the Midwest, especially Wisconsin. And these are small rounded hills that were created by glaciers depositing dirt and rocks and so on a place on the bottom of the glacier. And there's another picture of a kame. And as the Great Lakes, as the last ice age was melting, it actually increased what we now know as the Great Lakes significantly more than what they are now. So this is what it would have looked like about 10,000 years ago as the Great Lakes were forming, and they even had large lake plains that spilled beyond Lake Huron and Lake Michigan in Ontario. And a lot of what is now in the Midwest, including a lot of the central part of Michigan, would have been covered by a shallow part of the lakes that were linked to Huron or Superior or elsewhere. So the Great Lakes were actually significantly larger than they are now as the glaciers were melting. Out west, glaciers at the height of the Ice Age, these lakes weren't directly caused by the glaciers, but during this time period about 20,000 years ago, there was more precipitation in the western parts of the US, and there was a lot more rain and more water. So they did have large lakes out west, including Lake Bonneville, which is the remnants of the Great Salt Lake in Utah, is what's left of Lake Bonneville. But also parts of Nevada, low-lying parts of Nevada had lakes as well. Now we have just a small number of lakes out there. But Lake Tahoe, for instance, is visible here. But 10,000 years ago, there were actually some fairly large lakes caused by precipitation because of a cooler environment with more rain out west than there is now. Landforms and landscapes of mountain glaciers. We talked about continental glaciers, and we'll talk a little more about mountain glaciers. This is a glacier in New Zealand. You can see that this glacier has crevices or crevasses, and then there's a new light layer of snow that has fallen on top of those crevasses. And this is a picture of an island in the Arctic part of Canada from space, and you can see very clearly these large valley glaciers that have formed on this particular island. Those green areas are glaciers that have formed in valleys that kind of are moving towards the Atlantic Ocean. So North America has numerous large mountain glaciers. South America has some, but not nearly as many. The Southern Hemisphere doesn't have nearly as many glaciers as the Northern Hemisphere, except for Antarctica. But there are a few in the Andes Mountains and a few in some other parts of the Southern Hemisphere. But most of the glaciers, especially mountain glaciers, are in the Northern Hemisphere. So there are a very small number of mountain glaciers in Africa, just two, Mount Kilimanjaro and Mount Kenya. And New Zealand does have quite a few in the Southern Alps, a large mountain range they have in New Zealand. Lots of Lord of the Rings were filmed in New Zealand, a very beautiful rugged landscape. So some glaciers in New Zealand. And as far as Mount Kilimanjaro goes, these are some of the glaciers that are left on Mount Kilimanjaro. They've melted significantly in the last 30 years. Most scientists think because of global warming, most of the ice and glaciers on Mount Kilimanjaro in Kenya will be gone by about 2050. So unfortunately, warmer temperatures are shrinking some of the glaciers and the two mountain glaciers they have in Africa. The Alps, as you can see here, this is a picture of the European Alps from space. They have a large number of mountain glaciers. And some of the more famous ones is Mount Blanc. That's the highest mountain they have in the Alps. That's 15,771 feet. So Mount McKinley is about 5,000 feet above that. That's the highest mountain in North America, known as Mount Denali also. And then also the South Central Asian Alps. This is the Himalayas and the large number of mountain ranges they have there. This is the largest mountain system in the world, and it has a lot of Arctic ice. Sometimes this is called the third pole. There's so much snow and ice and glaciers formed in the Himalayas. It's what provides India and China with a lot of their water, a lot of the rivers that have made them so good for farming. So a lot of the high population densities we see in India and China is because of water coming from the Himalayan mountains that is trapped in ice and then melts during the summer. And Mount Everest is, of course, the largest mountain in the world, about 29,000 to 29,000, 29 to 29,035 feet. I've seen different estimates. Depends on what you consider to be sea level, but far and away the highest mountain in the world. K2 is the second highest mountain in the world, and that's in Pakistan. That's a lot tougher to climb, even though it's about 1,000 feet shorter. So erosional landforms of mountain glaciers. Again, erosion is when you have something getting broken down and knocked away, and deposition is when you have material that's being deposited. There are glacial troughs. Those are kind of large, low open areas that are formed by glaciers, as you see in A there. And then there also can be smaller glaciers that feed into larger glaciers called truncated spurs. And then you can have, they're sometimes called tributary glaciers. And then these large glaciers will often form over time U-shaped wide valleys that you see. And then some of these wide valleys have smaller valleys on the side of them that have water coming into them. And those are called hanging valleys, that you have lots of tributary glaciers used to be in them, and they melt and they form hanging valleys. And a classic example of a valley just like this is Yosemite Valley in Yosemite National Park. Looks almost exactly like the diagram we were looking at. And as you can see here, there is a waterfall on the right, and that is a hanging valley with water coming into it where there previously was a tributary glacier coming in. So perfect example of a large valley carved by glaciers. Other mountain landforms, this is a little more information on what glaciers can do to form not only valleys and rivers, but also kind of carve the tops of mountains. The diagram on the top is a mountain area before glaciation. And then as ice comes in and glaciers come down, they kind of break apart large parts of the mountain, leaving sharp ridges on the mountain called horns. And they gouge valleys, making them much deeper. And then after glaciation, you have the part that you see on the bottom right there, C. You'll often have Finger Lakes. You'll often have rivers, small lakes called tarns that are basically lakes that form up in valleys and mountains. And then you'll have arêtes and horns. Horns are basically sharpened mountains, sharpened by glaciers and so on. So these are some of the major landforms that you'll see caused by glaciers: horns, cureates, arêtes, and rock steps. So here are some examples of arêtes. Arêtes are razor-sharp, jagged rivers that rising above glacial troughs. These are some arêtes that are in South America. And as you can see here, you have these mountains and you have these very sharp peaks. Those are sharp because they were kind of carved by glaciers. And these are different ones in the southern hemisphere in the Andes Mountains. So again, this is more information on landforms caused by glaciers. Tarns are those rivers you'll see on the top right that are formed when you have an area high up in the mountains that are gouged out by the glaciers and then melt, and then you have mountain lakes that form in them. And maybe one of the most interesting are fjords. Fjords are very large, deep, relatively narrow, elongated ocean inlets that go all the way to the ocean. And then when the ice melts, the ocean actually starts coming back into that valley. So many of these fjords are actually salty and brackish for the first 100 miles when they're near the ocean, and then they slowly become more fresh as you go up them. So fjords are common in Norway and some other parts of New Zealand and elsewhere. This is one of the more spectacular fjords they have in Norway. So basically deep river valleys with water that have been carved by glaciers. So when you have glaciers forming, this is an example of a trunk glacier, the main one, and a tributary glacier kind of moving in and meeting up with it. The diagram on the top right here shows how a trunk glacier and a tributary glacier meet up. The tributary glacier is smaller, so it's kind of in the top right part of the trunk glacier, which is larger. And so that picture is a cross section of a trunk glacier meeting up with the tributary glacier. And then they can often leave deposits of outwash, lots of fine particles of rocks and sand that are kind of left at the bottom of the glacier. And then we talked a little bit about moraines and other things. So rock flour is ground up, finely grained sediment that's deposited by glaciers. And again, we covered most of these. This is what a landscape might look like after a glacier leaves, and it has all those different features that we discussed. One of the more interesting landscapes is the periglacier environments. These are basically environments that are not on glaciers, but kind of nearby glaciers, usually in tundras and very northern parts of boreal forests. They have lots of unique landscapes and so on. This particular picture is a summer Arctic in the coastal plains of Alaska. And the reason why you have that water pooling there is because the ground in this picture is permafrost. It's permanently frozen. So if there is any rain or there's any melt, it can't seep into the ground because the ground below it is frozen. So you have these odd small lakes or pools of water that form because the water can't drain into the ground below it. This has been an area, the periglacial region, that's been very hard for people to settle. Occasionally, people go to Alaska and try to mine in the late 1800s, and they try to make do in this difficult environment. This particular picture is of a house that was built on permafrost. Then when the house was heated and warmed up, the permafrost melted, the house sunk a little bit, and now it's starting to break up because it's sinking into the ground. So it's difficult to build infrastructure in these kinds of environments. This is a road in Alaska that was built in permafrost, and again, if it heats, it can expand and then contract, and it can break up roads. It's difficult to build in these rugged environments. This here is a cross-section of what typical ground often looks like in these glacial, periglacial areas. You'll often have an active layer, and an active layer is a layer above the permafrost table. This is a layer that is not frozen, or it's only frozen a small part of the year. Below that is the permafrost, and often you'll have water above an active layer, and below a lake, the area underneath that lake is called a talus. That's basically an area below a body of water that's active and not permanently frozen. Here's a little more information on permafrost. This particular picture shows parts of the Arctic that are continuously permafrost in white. The light blue is zones of discontinuous permafrost, meaning those are areas that can be permafrost or occasionally are not, depending on the time of year or depending on the conditions. And then in blue, you see zones of alpine permafrost. Those are areas outside the Arctic, but high up in mountains that have permafrost all or most of the year round. So frost action, as the earth in these areas thaws and freezes and thaws, it can actually cause something called frost heaving, and that can actually push up different boulders from the soil up to the surface of the soil. These big rocks you see there are boulders that have been thrust upwards from frost heaving. Again, the thawing and contracting can actually push objects in the soil up to the surface. And then frost creep is kind of the downhill movement of particles, similar to creeps that we studied earlier, where you have a hill that's slowly moving down and then the trees and the tombstones sometimes tilt. That can happen in areas that are cold as well, and that's called frost creep. Other unusual landforms you see here is often you'll have large chunks of land that freeze, and when they freeze in the winter, they kind of contract. And then in the summer, those cracks that are formed when land contracts can fill up with water due to rain or glacial melt. And then when that water gets in these cracks and freezes, that can cause frost wedging that can further break apart these. So you'll occasionally have landscapes where you have unusual patterns where the land itself is kind of broken into these unusual, almost square-like shapes, and that's caused by the surface freezing and contracting, water getting in, freezing into ice, and then breaking apart and expanding the cracks continuously. Other unusual things you'll see called patterned ground, and these are rocks and debris that are shaped and sorted into unusual formations due to the wind or frost action or some of the other things that we've talked about. So you will often see unusual landscapes like you've seen here, where the rocks seem to form unusual patterns caused by the different environments related to freezing and thawing and wind in the area. Another unusual landform are pingos. There's an article for this particular chapter that talks about these. These are large elliptical shaped mounds. They look like hills, but in the inside, instead of dirt or bedrock, it's actually ice. So it's a large bubble of ice that's kind of coming up, pushing up the land above it. And those unusual formations are called pingos. And this region also has rock fields, which we've studied in other areas. Those are just large chunks of rocks that kind of form at the bottom of areas prone to avalanches or rivers or glaciers or so on. So glaciers are retreating, and as you see in these pictures, the glacier in 1980s on the top, and then the same glacier in 2005 is significantly smaller. And on the bottom left, the Araparo Glacier in 1898 compared to the same glacier in 2003. So due to warming temperatures, glaciers almost all around the world are retreating, some quite quickly, especially in the Arctic. Permafrost in Arctic areas can have methane gas that gets trapped inside of ice bubbles. And you can go to some of these ice bubbles where you'll see these bubbles forming under the ice, poke a hole in them, light it up, and then methane will come out of it and you can actually light it on fire. So it's an interesting trick, but it kind of shows that as a lot of this permafrost thaws, it's releasing methane that was frozen in the permafrost that goes into the air, and that only accelerates global warming even more, which would be an example of a positive feedback loop. So in addition to glaciers, wind can also be a major geomorphic agent, meaning it can kind of shape the landscape as well. The picture here is the Tibetan Plateau. The dunes in this picture are moving from the left to the right, but the small little ripples you see on top are actually caused by a small storm where the wind was moving in the other direction. So you can have dunes where the majority of the dunes are moving in one direction, but occasionally the sand on top can be pushed back in the other direction. So areas that are shaped by sand erosion are called Aeolian. Basically, that means kind of shaped by sand. Where you have an area where there's more vegetation, it anchors down the sand and prevents erosion. There isn't as much sand being moved around. Humans can also impact and accelerate erosion in desert areas. We talked about that with building roads, or animals eating vegetation causing erosion. Prairies on the edge of deserts are often turned into deserts because of poor water management policies or overgrazing. So humans can accelerate and aggravate desertification and the erosion of steppes by turning them into deserts. But yeah, wind is a major player in shaping the earth, not as much as water or glaciers, but still fairly significant. This again is a picture in the Jara Desert in central China. You've probably seen camels, and you probably see the one-humped camels. Those are called dromedary camels or Arabian camels. But in Central Asia and in China, they have these two-humped camels called back-train camels or two-humped camels. So these are unique to the colder deserts of Central Asia as opposed to the hotter deserts of Arabia where you have the one-humped camels. So there are just those two species of camels. So with wind erosion, wind speed is very important. The stronger the wind speed, the more erosion it can cause. And the surface roughness of the land will slow down wind speeds and slow down erosion. So trees, vegetation, and grass will slow down erosion caused by sand. And sand is strongest close to the surface. And as you go up, sand loses its power. This is kind of a cross section of it imagines a dune, and these little red dots are sand particles being pushed around in the direction of the wind. And the greatest strength of these sand particles is about 6 feet to the surface. And then as you get above 6 feet to 7 feet, the amount of sand drops significantly and it doesn't have as much erosional power. So some of the unusual landforms that can be caused by sand is, as you see here, these are called yardangs, and these are rock formations. This is in the Persian Gulf near the Straits of Hormuz in Iran, where you have wind coming with a lot of sand from a specific consistent direction, and it kind of wears away the lighter rock, and the harder rock remains, and you have these strange linear rock formations that form. As there other kinds of erosional landforms in deserts are desert pavement. That's where you have a concentration of pebbles, usually in a windy area where the lighter particles of sand are blown away and the heavier pebbles remain in one spot. And then you have deflation, which is the removal of finer particles, which is what kind of helps lead to desert pavement where the larger particles remain. Also, occasionally you can have a desert where a hole forms for whatever reason, and then that hole actually becomes shielded from the wind, and it actually is a break from the wind. Those are called deflation hollows. So these three pictures here are examples of deflation hollows, kind of low-lying areas that can form in dunes that are actually out of the wind where the wind is not as strong. So this is a cross section of a dune. This is kind of looking at one, if you were to look at it from its side. And here you have wind coming from the left towards the right, and the wind pushes the sand up over the dune, and then it falls on the leeward side or the slip face of the dune where it's out of the wind, forming dunes. And then the windward side is always more gently sloped than the leeward side, which is sharper. So the wind is a little slower low to the ground in this case, and then the wind speed is faster as you get higher up. And then this is sort of how dunes can move slowly over periods of time. An erg is a really large area of sand, like a large sand sea. If you've ever seen any Star Wars movie, they have lots of them set on Tatooine. That might be an example of an erg. They have this massive, what looks like almost an ocean of sand that's often featured in them. And then the morphology of dunes includes windward slope, a crest, and a slip face on the leeward side of the dune. And then small ripples can form on the tops of them as well. So although dunes are formed all over the world, there are some unique patterns that seem to form on sand dunes, no matter where it is, whether it's in the US or Central Asia or wherever. It's common to have these four distinct patterns of dune: Barchan dunes, traverse dunes, longitudinal dunes, and parabolic dunes. And Barchan dunes are basically dunes where you have the dunes forming U's, and the pointy parts of the U's are going in the direction of the wind. You often have those in areas where there's strong wind but relatively limited sand supply. Traverse dunes are these sort of hilly dunes that look like waves, and the wind is perpendicular to the dunes that form. That indicates large sand supply and winds coming from one direction. Longitudinal dunes form where you have winds coming from multiple directions, and the longitudinal dunes form in the same direction that the prevailing winds are generally coming from. And then the parabolic dunes look a lot like the Barchan dunes, but kind of reversed, where the pointy parts of the dune are facing into the wind and the more curved parts are going with the wind. So those are often points that are anchored by vegetation, and then they can develop blowouts, meaning kind of holes in the sand that are sheltered from the wind. So these are four distinct sand patterns that you see in dunes all over the world, even if they're far apart. Here's a picture of Barchan dunes. Again, you can kind of see these U-shaped formations that form in the direction of the wind. And another important item related to sand and deposition is loess. We talked a little about this before. Loess is a German word for loose, and this is the real fine powdery accumulations of soil that are in parts of Central Asia, South America, and the Midwest, where wind has deposited large amounts of very fine dust and sand and dirt that have accumulated into very thick fields of very rich soil that can retain moisture very well, but are also very vulnerable to erosion. And these loess deposits are very good for farming, which is why where you see on this map, there are thick continuous loess deposits and thin continuous loess deposits. They often go along with some of our best farmland. And it's formed by a slow accumulation of small dust and dirt particles that have stacked up over centuries. China has a huge loess plateau in the northwest part of China. It's provided them with a lot of very good farmland. Sometimes these layers of loess can be hundreds of feet thick before you get to the bedrock. So it's been a big advantage for China to have large amounts of rich farmland in the eastern and northern parts of their country. So coastal processes. Basically, this here is a picture of the Oregon coast, and this is a high relief picture, which means there's a large variation between the low parts of a landscape and the high parts. You could have a spot that's high up in altitude but low relief, like a plateau where there's little variation in the land, but it's fairly high up. Or you could have the opposite, a high relief area close to the ocean like we have here in Oregon, and much of the western coast is like this. So where you have strong winds and you have erosional forces, you often have rugged landscapes. And where you have areas that are more out of the wind, like the Gulf Coast or parts of the east coast of the Atlantic, you have depositional landscapes where you have gentler water and more sand and less rocks and more continuous beaches. So coastal processes shape landscapes along major coasts. Because coasts are good places to be for commerce, you're integrated into the global supply because you're close to the ocean. You often have good farmland. These are areas that have lots of humans and people that live on them. I think I heard about 70% of Americans live within about an hour of the coast or the Gulf. So in many countries, Australia is notorious for that. Almost everyone lives within an hour of the ocean. Very few people live in the interior. So these coastal areas often have very heavy populations. You can think of New York, Miami, and Shanghai, and a lot of other massive coastal cities. So studying the impacts of coastal processes is very important for scientists so they can better understand how they affect the people who live there. So an area along coasts or where the water is relatively shallow is called a littoral zone. You might have heard of the phrase littoral ship. Those are ships in the US Navy or other navies that are designed to operate in relatively shallow water near the coast. Sometimes they're called the brown water fleet, while deep water vessels are called the blue water fleet. So aircraft carriers would be blue water, and maybe small patrol boats would be littoral ship or brown water fleet. And the coast itself is the strip of land where the coastal processes go on. It's a fairly large general area. The shore is a narrow belt of land where the land meets the water, and the shoreline is the actual contact point between the water and the land. So coast is more general, shore is a little more specific, and shoreline is very specific where the water meets the land. So waves are a real important part of coastal landforms. This is the most important agent forming the uh, different landscapes you see along the oceans. Waves depend on the velocity, that's the speed, the direction and persistence of the waves. If you have an area where waves are coming from a specific direction continuously, that can influence the landscapes. The duration, how long the waves last. You might have strong waves, but they might not last real long. And then something called the fetch, which you might not have heard of, but that's basically where do the waves originate from, usually referring to a very large open body of water without anything to disrupt or break up the waves. So large ocean waves usually are formed in large open bodies of water like the Atlantic and the Pacific, and not the Gulf of Mexico, because you need large open areas to build up large waves. And those birthplaces of large waves are sometimes called the fetch, sort of the breeding ground for large waves. So wave properties, waves have a crest at the top and a trough at the bottom, and then a wave length, which is the distance between the two crests in between a wave. So the height is the vertical distance from the crest to the trough. The wavelength, again, is the distance from one crest to another. This is actually similar with sound waves and light waves as well. And the wave period is the time required for two successive crests to pass a fixed point. So kind of how long it takes to go from one crest of a wave to another. So it might look like if you're looking at a wave, a specific small parcel of water is traveling with the wave, but that's not really the case. If a typical body of water will move in a circular pattern where a wave will come and then it will kind of move up a part of the water and then it will move down again. So the water continuously moves in cycles and the waves might move, but if you had a leaf that you placed on top of a wavy lake, it wouldn't go along with the top of one wave. It would kind of stay in one spot and different waves would pass it by and it would stay relatively stationary. So these circular patterns that you have in the water become less and less significant as you get further down. And generally speaking, the motion is negligible when you get about half the length of the wavelength down below the water. So if a wave length is maybe 10 feet from one peak to another, below 5 feet, there's very little motion in the water and it's fairly stationary. So wave agents are waves against the shore. This particular diagram shows waves that approach to the shore. So you'll have a wave, and then as it gets to the shore, once it gets to a point where the land is about half the distance between the length of the wave, it starts to affect the wave, and the wave becomes a little more compressed and condensed and speeds up and then forms into a peak and then breaks. That's called wave break or breakers. So you have waves breaking where you have the bottom of the ocean or lake getting shallower and shallower, and that's where you have the waves breaking. So this diagram kind of shows that. The top right picture shows evenly spaced breakers or evenly spaced waves washing up against the shore there. And waves don't always come towards the land at head on. Sometimes they'll come in at an angle depending on the wind. And where you have a wave that's coming towards the shore at an angle, a part of the wave will hit the shallower part first, and that part of the wave will slow down while the longer waves will continue at their typical spot. And that can kind of cause the wave to bend, as you see here, into this sort of U formation. So it's common to have this this bending of waves as they approach the shore. And where you have this, you'll often have what's called a longshore current. And those are the currents formed along the shore where you have these waves coming at an angle, kind of hitting the shore. So you'll have these currents where you have waves coming in at a sort of a diagonal area. So here's kind of a picture of a shore with waves coming in at a diagonal area, where you can see here, I think this is Lake Superior. And where you have a rugged coast, where you have bays and parts of the land that stick out more, the lands that stick out more are actually hit more forcefully by the waves, and the bays, because they're shallower, are a little more protected. They're more likely to have sand and soil deposited in them. So where you have a landscape like this, over time, the bays will come out because of deposition and sand being deposited, and the peaks and the headlands, as they call them, will be worn out. So over time, it's common for jagged coasts to become more smooth and have less variation in headlands and bays and kind of even out. So this is a diagram of waves crashing into a rugged shore. And I like to use Michigan as an example. This is an example of a bay along Picture Rocks National Lakeshore, and a headland coming out from the land. And as you can see, it's getting hit pretty hard by those waves. The rocks in this area is fairly hard sandstone, so it's somewhat resistant to erosion, but given time, those headlands that are popping out from the main part of the land will break down and wear down, and it'll turn into a much more smooth coast like you have along much of Lake Michigan. So as you have waves coming into the shore, you have a lot of the same waves kind of pulling back in something they call rip currents. And that pulls back some of the sand that would otherwise be deposited. The picture on the top right here shows a typical beach if it had some sandbars that were either above or below the water. And then you'd have the waves that would come crashing over those sandbars. And then as it pulls back, they would often travel in between the spaces of those sandbars, creating rip currents. And the rip currents can be fairly strong. If you were ever pulled in or out to shore from a rip current, just remember, swim parallel to the beach and they will eventually subside. Don't try to swim directly into shore. Swim parallel to the beach and eventually you'll get out of the rip current and you can make it back to shore. But they can be fairly strong. On the bottom, you'll see the white areas are areas where you have an intense rip current along the shore there. So some ways of trying to prevent erosion, especially in areas where you have a lot of development, you have a nice apartment or beach or infrastructure, you don't want the sand to wear away. They'll build barriers, sometimes called groins, and these are basically things that stick out perpendicular to the land, that stick out at a 90-degree angle into the water. And they do help prevent erosion to some degree, but they also can prevent sand from being deposited in other parts of the sand as well. So you have to use them carefully. They're not a cure, but they can slow down erosion to some degree. This is Miami Beach here, and Chicago has planted a lot of these along their coast. And you can see here on the top right, Chicago's building these little groins, as they call them. And then on the right, you can see after several decades, sand has naturally built up in some of these that are jutting out, and it has created a nice beach. But as you can also see on the opposite side of these groins that are sticking out, the sand is kind of small at first, and then it builds up as it hits its own groin there. And then this kind of demonstrates that it's good at capturing sand, but it kind of prevents sand from flowing further down the lake if you don't have one of these. So this is, again, Chicago. They have a lot of very nice beaches in Chicago, actually. So tides are caused by the moon and the sun, and gravity from the moon and the sun, specifically the moon, but to a lesser degree the sun. And there are basically cyclical rise and fall of sea levels. You have to get tide charts to know when an area is going to have a high tide or low tide, but generally they have two high tides and two low tides in roughly a 24-hour period. And where you have the moon and the sun aligned, you have a strong gravitational pull towards the moon and the sun, and you have what are called spring tides, the very strong tides. And then when you have the moon and the sun that are perpendicular to each other, you have a weaker peak tide called the neap tide. So those are the weaker of the two tides, and then it can vary significantly. And having major changes in the tide can also increase erosion. Tides don't hit everywhere equally. If it's a large open area, there's relatively little effect. I was in the Keys about 2-3 months ago. You could barely notice any change between high tides or low tides. But if there are bays and protected areas that go into the ocean, those are areas that you'll often have huge tidal changes. The Bay of Fundy in Nova Scotia in Canada, a little bit north of Maine, is famous for huge changes in tide. As you can see here, you can have a change of 50 feet or 15 meters at the part of the bay that's furthest away from the Atlantic Ocean. And you can see it's 20 feet near the mouth of this bay. But this is really famous for having huge swings in the high and the low tide. Here it is at high tide on the bottom and then low tide on the top. So major variations in the tide on this specific bay. So storms can cause a significant amount of erosion along coasts over a short period of time, especially hurricanes and other major storms. And these are things that can significantly modify the coast in a short period of time. Waves can aggressively attack coastal features like pillars or arches and so on and break them down. And high tides can aggravate these conditions. If you have a major storm that hits at high tide, it can be really damaging to a city or area. Also, things that can change land formations are crustal movements. We talked about plate tectonics, and a shore can be pushed up or it can be worn down depending on if it's near a specific kind of plate. If you have a coast along Chile or South America, that is a subduction zone where the Pacific plate is being pushed underneath the South American plate, pushing up the land and therefore pushing up the coasts as well. And then you'll have areas like Texas and Louisiana, where there's lots of sand being deposited by the Mississippi River that are fairly low lying, that don't have major storms because they're protected by the Gulf usually. And then those are areas that are examples of sometimes sunken landscapes or where sediment is playing a major role. So coastal landforms and landscapes, this particular picture is of a natural land bridge in Aruba, and that's in the Caribbean. And there are two major categories of coastal landforms, and that's depositional and erosional. Depositional means that sand is being deposited there. Erosional means that the rock and the sand is being worn away. But you can have a coast that can be affected by erosion and deposition at the same time. So it's not always just one or the other. You can have a coast that has a little bit of both going on. And this here is a cross section of a typical beach profile. The near shore is the submerged during low tide. That, of course, wouldn't affect the Great Lakes, but that would affect the ocean. The foreshore is covered by high tide and exposed at low tide. So the foreshore is partly underwater some of the time and then not underwater some of the other time. And then the backshore extends from the high tide to the first dune or berms. And that is basically areas that are permanently on land under normal conditions, as you see on the left part of this here. So the foreshore is what we might think of when we really think of the beach. That's the land that's partially underwater and partially above water, depending on the tide. And as you see here, it's common to have a sandbar form a little bit off of the main beach, and then also a longshore trough in front of that sandbar. That's something you see in Lake Michigan a lot too. You kind of go out, then you go out, and then all of a sudden it gets a little shallower as you walk a little further away from the shore. So these longshore sandbars are common in many large bodies of water. So this is a beach in profile. You can have, usually when you have summer weather in beaches in Lake Michigan or the ocean, the summer is usually a little more gentle and you have land being deposited by gentle waves. And then during the winter, you have rougher waves and bigger storms, more erosion, and much of the beach is broken down and pulled back into the water. And that can shrink the size of the beach during the winter and create a longshore sandbar a little bit off of the main coast. So this is an example of how you can have changes based on the season in different beaches. They can grow during the summer and then erode during the winter. So for coastal dunes, there's a strong sea breeze that moves to the beach, and that can create some sand that gets kicked up. And vegetation can cover and anchor down those sand dunes so they can build up over time. If there's no vegetation, then often the sand is kind of blown away, but vegetation can anchor it down and help it accumulate. And it's common if you have a coastal area, especially in depositional areas where sand is being deposited, to have a sand spit. Basically, these are sand deposits that kind of form coming off of a pillar or something coming out of the land itself. And then you can see here on the diagram, there's a spit that's coming out, sort of covering over the water. And then if spits extend too much, they can completely enclose what used to be a bay and turn it into a lagoon, kind of completely protecting it from the water. And that's when you have a baymouth bar form. That's when a spit extends to the point where it completely encloses a body of water that used to be a bay, and then that becomes a lagoon. And then you also have barrier islands that can form along depositional coastal landforms like we have along the east coast of our country, especially along North Carolina. This is sand spits and sandbars. This particular picture here is Sandy Hook, New Jersey. So that's a barrier island off the coast of New Jersey. And then this picture here is a sand spit called Point Pelee National Park. This is a long point of mostly sand that extends into Lake Erie on the northern part of Lake Erie. And I actually have been here. There's this real long, narrow strip of sand that's a sand spit that extends past that green point of vegetation you see on the top right. And this particular peninsula is really popular with migrating birds because instead of having to fly around all of Lake Erie, they can fly to the very end of this peninsula and then fly to a series of islands called the Fighting Islands that are in the western part of Lake Erie and land on them. And then they can cross Lake Erie while taking breaks on the little islands at the end of this peninsula here. So they can fly a lot less by flying to the very tip of this peninsula and then flying over Lake Erie, stopping at the little islands until they get to the southern part of the lake. We also learned there was about a tumbelow. And we'll go back a little bit. A tumbelow is basically when you have a sand spit that extends out and links up with an existing island. Those are a little unusual, but there's a fairly famous one in Grand Island. This is an island off the coast of Lake Superior near Munising. If you've ever been to Munising, this is near all those beautiful rock formations they have. And it's near Lake Superior, Lakeshore. And this is basically a tumbelow that formed on Grand Island and then linked up with what had previously been its own island and then was nicknamed the Thumb. So now it's called the Thumb of Grand Island. But that's an example of a tumbelow there. Yeah, Picture Rocks National Lakeshore is where Grand Island is. So this is a cross section of a barrier island. They typically have the part that's facing the ocean that's at sea level. Then as you go inward, there's a beach. Then there's typically dunes. Then on the opposite side of the dunes, where it's a little protected from the wind, you often have shrubs and vegetation and then mangroves. And then as you extend further towards the land, you have the lagoon, which is usually a completely enclosed or largely protected body of water. If it's not completely enclosed, sometimes it's called a sound. If it's completely enclosed, it's usually called a lagoon. So this is kind of the cross section of a typical barrier island that you might see in the Outer Banks or elsewhere. So this is a picture of the Outer Banks from space. These are a series of very famous long barrier islands off the coast of North Carolina and Virginia. They're very popular with tourists. I've gone there a couple times. It's just beautiful, fabulous, great beaches. If you want to fish or do something where you're not right on the ocean, you have the lagoon or the sound on the land side. And then if you want to go to the beach and you want to have huge beaches and wind and so on, you have the ocean nearby. So it's a really beautiful, fun spot to be. So erosional landforms, we talked about depositional landforms. Now we talked about landforms formed by erosion. These are areas where you usually have stronger storms and more of a breaking down of land and less deposition. So these areas often have sea cliffs. Those are basically just large cliffs that are hit by waves and broken down by erosion. You'll often have wave platforms at the base of cliffs. You'll have sea arches forming. Those are basically large rock arches where you have land being broken down around them, leaving harder rock that's in the form of an arch around. And then sea stacks. Sea stacks are often sea arches whose arch has collapsed and then left them as kind of individual pillars of rock. So on the right, you can see examples of those landforms. This here is an example of a sea cliff, one of the taller ones around. These are the chalk cliffs of southern England. So chalk is not a particularly hard rock, so these cliffs are very vulnerable to erosion, but because they're so huge, even if they wear down because of erosion, their size means they'll be around for centuries. But what you see there is chalk, the same things that you write with. It's a very soft, natural rock that will wear away with erosion, but in this particular case, their massive size will prevent them from completely eroding anytime soon. So real pretty, that's in southern England. Some of these rock cliffs are 200 or 300 feet high or even higher. So this is an example of some of the arches that we talked about. This again is Lake Superior, Pictured Rocks National Lakeshore. And you see water kind of breaks away the softer rock, leaving the harder rock to remain. Those could eventually be broken down and form individual pillars or be worn away entirely by erosion. So we talked a little bit about how coasts can either be emergent coasts or submergent because they're part of natural plate tectonics like the rest of the world. And if you have an area like we talked about with Chile in South America that's being pushed up, that can lead to changes in landscapes where it continues to get pushed up. That fights against erosion because you have rock that's being worn down but simultaneously being uplifted as well. And submergent coasts like the Mississippi Delta and areas, sometimes they're called drowned coasts. And these are areas like Galveston, Texas, which was hit by a major storm in 1900 and is sinking because of a combination of rising sea levels. And also a lot of urban areas are built on river deltas because that's often where rivers meet the ocean. And that can also cause problems because cities themselves are very heavy. Think of all the concrete and all the skyscrapers and how much that weighs. So you have massive urban areas with skyscrapers and roads. That adds weight, and that can actually cause an area built on soft land near the coast to slowly sink. Venice, Italy is an example of that. Venice has been sinking for centuries, and usually the residents just keep building higher and higher on top of the buildings that they already have there. But that's an example of emergent coasts, ones that are being pushed up because of tectonic action, and submergent coasts that are being worn down by erosion or rising sea levels or sinking cities. So finally, some of the newest land we have are islands caused by volcanoes, and Hawaii is a good example of that. And volcanoes, again, we studied this a little bit, but they'll explode. The lava will come over the island. It'll go down into the water where it will cool very rapidly, like we have in Hawaii. And you'll often have a volcano, once it stops erupting, will form a coral reef. Basically, the volcano itself starts to erode, as you see in B, but the ring at the very edge of the volcano, because it's lower, it's not as vulnerable to erosion, and it will remain even after the center part has completely collapsed due to erosion. So on the A, you see an island that's being formed. B, you see it wearing down because of erosion. And at the bottom, you have what's called an atoll, and that's basically a ring of what used to be the edge of a volcano that's now a long, narrow island with a protected lagoon in the middle of it. So these are examples of changes that can happen due to volcanoes. Mangroves often form where you have atolls or where you have rivers meeting up with the ocean. And those are actually very good at kind of anchoring down the coasts and blunting the energy of waves. Some people want, many states actually have laws that protect mangroves. You can't pull them out or remove them because they are so good at stabilizing the coast and preventing erosion. There are also nurseries for small fish and other animals. Large fish can't get in the tangle of roots in mangroves, so they're a nursery for small animals. This particular picture here is Bora Bora in the South Pacific, and it's a perfect example of what we saw here in the second slide here. As the volcano went extinct, it's slowly wearing down. So you can see here the remnants of what used to be a volcano and an atoll forming around it, but this at least still has an island in the middle. Hundreds of thousands of years, that center island will be worn down and eroded, and you'll just basically have the atoll on the outside. But at the moment, it's a real beautiful destination in the South Pacific. You can also see there's a cloud that forms right above the island. It's clear blue skies all around, but right above the island you have a cloud forming. That's because you have moisture from the air kind of moving over the ocean. It goes over the land. There's an increase in temperature because the land is hotter than the ocean, and that causes clouds to form because of the change in temperature. And again, that's Bora Bora. Haven't been there, but I'd like to go there sometime. And that is it for our final unit. If you have any questions, you can send it to me in the form of a text or ask it in the form of a microphone if you have one. If you think of something later, you're welcome to email it to me. Otherwise, it's been great working with all of you. I hope you've enjoyed the class, and you have until the 29th to turn in any work you have. Technically, the class ends on the 29th. I'll give you to the 30th, but try to have everything on the 29th. And thank you for joining me, and have a great weekend.